In example 12.8, we are provided with a function given by f of x is equal to 3x squared plus 2x minus 2. And we're asked to first graph the function on the Cartesian coordinate plane. So looking at the function, I'll notice that it is a standard form quadratic, ax squared plus bx plus c, where a would be equal to 3, b is equal to 2, and c would be equal to negative 2. The domain of this function will be all real numbers. But in order to get the graph completed, I need to know the location of the vertex. Using h equals negative b over 2a, we can calculate this. Negative 2 over 2 times 3, so that's negative 2 over 6, reduces to negative 1/3. And to find the value of k, I will take the value of h and I will plug it in to the function equation, f of negative 1/3. And this is going to get a little bit challenging since we're working with a rational number here. But we'll plug in negative 1/3 and we'll work on simplifying and eventually getting a single value for k. So now we have to go through the arithmetic. I'm going to square negative 1/3, square the top, square the bottom, get 1/9. When I multiply a whole number times a fraction, it only multiplies to the top, so that makes it negative 2/3 minus 2. Keep simplifying. 3 times 1/9 will reduce to be 1/3 minus 2/3 minus 2. So that's negative 1/3 minus 2. Now when I'm adding and subtracting fractions, we should be aware that a common denominator is required. So I'll have to treat this whole number as if it's over 1, multiply top and bottom by 3. So that gives me negative 1/3 minus 6/3 for a grand total of negative 7/3. So my vertex is located at negative 1/3 comma negative 7/3. So looking at the Cartesian coordinate plane, I'll come over here to negative 1/3. On the x-axis, it'd be about right there. Negative 7/3 would be negative 2 1/3. So I'll go a little bit below negative 2. Negative 2 1/3 would be about right there. So where those two intersect just happens to be right here below the number negative 2. So that's the vertex, which means that there is an axis of symmetry that runs right through the vertex vertically. And the other thing that I'll notice was that the a value is equal to 3, which means that there is a vertical stretch. Now, I normally don't have a problem applying a vertical stretch because of the work that we've done with transformations already. However, it is going to be particularly difficult to do because the vertex is not starting on integer values. It's starting at negative 1/3, negative 7/3. So rather than trying to graph the parabola from here, I'm going to find two other points, actually 3 other points, that are going to help with getting that, getting some more to the shape of the graph. So the next part B, I can actually do part B. Part B is wanting us to state the domain, and the domain for this function is all real numbers. And we can also state the range. Even though we don't have the graph, we should also know that because the a value is positive, the graph is going to open up from the vertex. So even though I don't have an accurate picture, I have enough information to know the range. The range is going to have a lower boundary of negative 7/3, and it is unbounded in the positive infinity direction. So negative 7/3 to infinity for the range. Now let's look at part C. This is where we're going to get some nice help here for the graph. So I'm going to go ahead and erase what I have here for the graph. Just leave the vertex there. We'll come back to it. Probably the most involved calculation here is going to be the x-intercept calculation, but it's also possibly the most useful calculation that we can do. So anytime you're trying to do an x-intercept calculation, you should just set the function equation equal to 0. So that means that we would have the statement 0 equals 3x squared plus 2x minus 2. Now this equation in its current state is not particularly easy to solve because we have two different places where we have x. It's quadratic. The terms are different, so they can't combine together. But we do have the value for h and k over here when we did the calculation for the vertex. There's h, there's k, and up at the top we have the value for a. So we have all the pieces that we need to write this in vertex form instead. So let's write it in vertex form. 0 is going to equal 3 times x plus 1/3 squared minus 7/3. It's the same equation, just written in a different form. Same function. But now I can take a slightly different approach. I'm going to add 7/3 to both sides to get 7/3 is equal to 3 times x plus 1/3 squared. Then I'm going to multiply both sides by 1/3, or you can say divide both sides by 3. Either way, you should get 7/9 is equal to x plus 1/3 squared. And then when you take the square root of both sides, you'll take the square root of 7/9, and then that will just be equal to x plus 1/3. Have to be sure to put plus or minus in front of the square root. That's one of the rules behind taking the square root of both sides. And then I'm going to do a couple of things on this next step. I'm going to subtract 1/3 from both sides, so I get negative 1/3 plus or minus. And then I'm going to take the square root, and I'm going to use a property of radicals that says I can apply the radical to the numerator and to the denominator separately. So I can call this the square root of 7. And then for the denominator, I'm not going to say square root of 9 because that would simplify to just be 3. So square root of 7 over 3 is equal to x. And if you're familiar with the quadratic formula, then what's about to happen will look very familiar. I have a common denominator, so I can just combine them together. Negative 1 plus or minus the square root of 7 all divided by 3 is equal to x. Now, those are the exact answers. For graphing purposes, I would need to know the decimal approximations. I would encourage you to use your calculator and check the decimal approximations. I have those here already. They are negative 1.2 as well as 0.5. So for writing down the exact location of the x-intercepts, I do want to use the exact answers. So I would say negative 1 minus the square root of 7 over 3, comma 0. That's one of my x-intercepts. And then there'll be another x-intercept at negative 1 plus the square root of 7 all over 3, comma 0. So that takes care of my x-intercept calculation. I can also do a y-intercept calculation. The y-intercept calculation is much easier. That can be done just by calculating f of 0. So by plugging in 0 into the equation, I will have 3 times 0 squared plus 2 times 0 minus 2. And that is all equal to negative 2. So I can write down 0, negative 2 as the ordered pair that represents the y-intercept. So that gives me 3 more points that I can use along with the vertex to get an idea of what this graph looks like. 0, -2 is going to be on the right side of the axis of symmetry. And then also 0.5. Now that's an approximation. 0.5 would also be on the right side. So I actually have enough points to be able to graph the right side of this parabola. It's going to look something like this. And on the left side, I have the point -1.2, should be about right there. And then I'll follow the curvature best I can. And you can see how, because of the points, the way they're laid out, it is a more narrow, stretched out version of the parabola. It's not your traditional parent function. It's a little bit stretched out, and that's because a is equal to 3. So that's a way that we can go ahead and alternative way of getting the graph completed without having to use the transformation stretching mechanism. So that takes us through part C. The other parts are pretty quick. Part D was wanting to know the relative extrema. There is a relative minimum, and that is located at the vertex, -1/3, -7/3. Part E, state the intervals of increasing, decreasing. We have increasing interval starting at the axis of symmetry, going to the right. So that would be -1/3 to infinity. And we are decreasing to the left of the axis of symmetry. So that would be -infinity to -1/3. And then finally, on part F, the equation for the axis of symmetry is going to be x equals -1/3. And that completes the analysis of this function.